Okay, so what we're going to do is, like I said, we're going to use Green's theorem to kind of help us interpret curl and divergence, and at the same time kind of use curl and divergence to get a better understanding of Green's theorem. And so that's why we kind of looked at Green's theorem, and now we looked at curl and divergence, so we're going to kind of come back and reevaluate Green's theorem just a little bit. Okay? So remember, Green's theorem states that if we have P and Q in, we had the assumption that we were in a simple region and they had continuous partial derivatives, and C is, a planar curve that's positively oriented, then we had the assumption that the line integral over C, that's not C, or dy, we said that's equal to the derivative over d of this kind of funny dq dx minus dp dy. Okay, so it was a relation between the line integral over p and q, kind of related to these partials over the double integral over the region. Okay, and so notice that if we think of F as a three-dimensional vector field, okay, we're thinking in three dimensions because we're letting the third dimension just be 0, then this integral here is also equal to the line integral over F, because that would be p dx plus q dy plus 0 dz. And so we can just kind of, not think about that. Okay, and so what we're going to do is we're going to try to use curl to help us interpret this a little bit. Because, I don't know, if you look at this right here, this dq dx minus dp dy, that actually occurred in the curl. And so we'll kind of look at what I mean by that. Okay, so let's look at what the curl of this vector field will do. So again, we have our vector field is p, q, and 0. And so remember, the curl of F is going to be the cross product of that del operator and F. So that was ddx, ddy, and ddz. And then we're going to have p, q, and 0. Okay, so for the I component, we're going to have d dy of 0 minus d dz of q of xy. All right, xy. Okay, and then for the j component, right here, we're going to have dz falling over here on p minus dx falling on 0. And then the k component is going to be, here's where we're going to have dx falling on q minus dy falling on q. Okay, so this is what the cross product is going to look like. And notice because, let's see, if we go back to right here, because we're assuming that P and Q are just, you know, in the plane. So P and Q only depend on X and Y because that's kind of part of the assumption of Green's theorem. And so that's why I use this notation here. So it's kind of just like with the warm-up. If we're taking the derivative with respect to z of a function of x and y, that's just going to be 0. So like right here, we're just going to have 0. And likewise, when we take the derivative with respect to z of this function x and y, we're just going to have 0. Okay? And obviously, when we take the derivative of the 0 function, we're going to get 0. So in other words, both the I component and the j component are just going to be 0. And then the k component, we can see, is going to be that dq dx minus dp dy. Okay? Does that make sense? And so, now remember that this line integral of our vector field, by Green's theorem, we already saw that that was equal to dq dx minus dp dy. But that's just equal to the vertical component of the curl. Kind of why this analysis that we have up here. And so what we can think of doing is, if we have the curl, which we know is 0, 0, and this term here, because the curl is a vector, and this integral is just kind of over this value, we have to think of a way of extracting this value from that vector. Does that make sense? How can we do that? What operator can we use to take a vector and turn it into just a number? So we could do the magnitude. That's a pretty good idea. But what else do we do? There's another way we can kind of think of doing it. Yeah, it's actually just like a projection, and we're going to dot it, and all we're going to dot it with is like we're going to project it onto the vertical like normal vector. Okay, and the vertical normal vector is just like 0, 0, 1. Okay, because that goes vertically. Oh. Yeah, so we just want a normal vector, or a unit vector rather, and it's going to be going vertically, and it's got a magnitude of 1. But we can just kind of rewrite this as the curl of f dotted with k, because k is kind of that general notion we have for we have I, j, and k. And so this is kind of what we end with. I think that's exactly what I have. Yeah. And so what this is saying is that the tangential component of f along C is equal to the sum of the curl of this whole vector field in this region. Okay, so let me kind of see if I can draw a picture of that in a very rough way. Okay, so we're just kind of thinking of a planar region right now. So we just have some surface down here, or some shape down here in the xy plane. And what that says is, if we think of having a vector field f, let me draw this, all these little tangent vectors here. Okay, so we have, it don't really looks like a fuzzy little ball or something, I don't know. So if we think of like summing up, remember that the right side of that was f dotted with dr. Okay, and what is that also equal to? Kind of think back when we first defined line integral. The work. That's equal to the work. Okay, and so the work that this force field does tangentially along this curve is exactly equal to how much this curve is, this vector field is rotating in that region. Does that make sense? So that's why we call it curl, because how much this force field, this vector field, is rotating this curve is exactly what we're calling the curl of that region. Does that make sense? I think after we look at kind of the other side of things with divergence, the two of these together will make a lot of sense. Okay, so kind of the whole point. Curl is just, if we think of adding up all the curls in this region D, that's going to be how much this curve is rotating based on that force. That's going to be the rotational force that force field is applying. And that's why it's the tangential, because that's going to kind of be rotating along the curve. Okay? So, like I said, once we look at kind of the other half of things, we will, I think it'll make a little more sense. Okay? So, that was with the tangential component, and now let's kind of do the same thing. Let's look at the normal component of the, and see if we can come up with some similar results. Okay, so we have, what we're assuming is we have some curve, here just in the plane. So we'll call this C. And remember that we can like cook up the tangent vector. It's just going to be x prime of t plus y prime of t in the j component. That's a common Okay. And then there was also kind of, we could go farther and turn this into what we call the tangent vector by making it a unit vector. And so all we did then was we divided through by the magnitude. Y'all remember that? That's kind of from way back in the day when we were talking about vector functions. But just like taking the derivative, all we have to do is take the derivative of each function, and then we just want to turn it into a unit vector by dividing through by its magnitude. Because then this thing is going to have a magnitude of 1. So it's just a unit vector. Okay? And then we also went through and figured out how to cook up the normal vector. And so I'm not going to kind of bog you down with the details, but we can, if we want to go through and show, we could show that the normal vector was equal to y prime of t over r prime of t in the I component, and then negative x prime of t, r prime of t, over r prime of t in the j component. Okay, so I'm making a little larger. Okay, and so what this is going to look like if we have well, I mean, it's quite a difficult computation, but that's what it works out to be. Yeah, on the normal vector it's y and then negative x. Yeah. And it's hey. Hey. I guess it's just I didn't move. now I'm just okay, and so what the tangential vector would look like, it would be going along this curve. And the normal vector would be perpendicular to that, and so it would kind of be pointing straight directly out of that curve. Okay, so this over here would be C, and this would be our A. Okay, so when we integrate just the line integral along R or along the curve C, we're kind of taking the tangential component. Remember, because the way we defined that was the integral of f dotted with dr is really the integral of f dotted with r prime of t dt. And so if we instead wanted to, oh man, I just copied this whole page. That's why. I bet I copied like 3 times. I'm going to delete it again. There we go. Okay, so if we instead wanted to integrate along the normal component, instead of integrating along the tangential component, then we would dot it with that normal thing. Okay, so let's kind of take a look at what this looks like. So whenever we're trying to integrate these line integrals, the best thing to do is always just turn it into our parameter, which would be t. And so we're going to be integrating from a to b f x of t, y of t. And then we're going to be dotting it with n of t, and then we're going to turn dr. Remember, we already said that that's equal to r prime of t. Okay, and so I'm going to write out what the vector is going to look like. So f is going to be the vector t of x of t, y of t, q of x of t, x of t, y of t, y of t, y of t, and then 0. And then we said that that normal vector was negative y of t, y prime of t. What was it? It was y prime of t and then negative x prime of t. Right. So we're going to have negative x prime of t. Those things are divided by the magnitude. And then 0 for the kind of third component. And then we're still going to multiply by the magnitude of our prime of t. Okay. So let's kind of evaluate what this dot product is going to look like, and then we're actually going to kind of switch back into this being a line integral, and then it's going to be like, Okay, so when we do the dot product, we're going to have t of x of t, y of t, times y prime of t. And notice that this is over r prime of t. Like both of these components are over r prime of t, but we're multiplying by the magnitude of r prime of t. So all of these are going to cancel. And so we just kind of like, that works out really well. And then we're going to have minus q of x of t, y of t, times x prime of t. Okay, and so what we kind of have to think of doing now is, remember, this whole thing is being evaluated with respect to t, so we kind of have a dt on both of these. And so if we want to switch back to just being the line integral over the curve, then what we have would be p times y prime of t dt, which would just be p dy. And here we have x prime of t dt, which would be dx, and so we're going to have minus q dx. Okay, so we kind of have to think of like distributing this dt. And remember, y prime of t dt equals dy, and x prime of t dt dt over dx. That equals dx. Okay, so we're kind of switching, dx too. We're switching back to being parameterized just with respect to, kind of with respect to our curve. Okay, and I'm going to rewrite this one more time in a, just kind of in a form that'll be a little more familiar. Okay, so now we have the line integral of some function dx plus another function dy, and what do we know we can always apply to this? We can apply Green's theorem. Okay, and so when we apply Green's theorem, we're going to have the double integral over that enclosed region D of our second function, the derivative of our second function with respect to x, minus the derivative of our first function with respect to y, which would be negative q, which is just going to equal the integral of dp dx plus dq dy. And what is that kind of? Do you recognize what dp dx plus dq dy is? The first derivative, the derivative of the first variable with respect to x, and the derivative of the second one with respect to the second variable. What does that exactly look like?
Oh, that's
Not quite the gradient, because we're talking about over a vector field. What's kind of the analog of the gradient over the vector field? It's just the divergence. So that's just the divergence of this function f. So that's kind of when we take the normal component and take the integral over it, it's equal to the divergence. Okay, so let's kind of like, I want to kind of compare these two results. Okay, so on the one hand, we've been looking at curl, and on the other hand, we've been looking at divergence. Okay, and so what the first kind of result we just got said that it is, again, if we sum up all the work that this vector field does tangentially going around this region, then that's going to be equal to the curl of the vector field within the region. Okay, so this is the work done by F around the outside of D. And we said that we kind of saw that that was equal the vertical component of the curl of the whole region. And so remember, the vertical component is kind of the quantification of the rotation in the plane, because that curl vector, because it's the cross product, it's kind of perpendicular to the plane of rotation. And so this vertical component of curl is going to be exactly how much this whole region is rotated. Okay, so this is like going to be the sum of the, I guess we'll call it horizontal. I'm going to put that in quotes. Horizontal rotation of F inside V. So the curl, that's why, again, we can kind of think of curl as the kind of the total, the rotation of the vector field. Okay, and then let's also kind of think of what we just saw with divergence. Okay, so we kind of have the same region, but instead we were looking at the normal component of like, you know, all these little normal vectors. And so we saw that good old osmosis. So we saw, you know, this would be kind of the work done by but instead of being around the region D, it's kind of outward, kind of that work done in the outward direction. Does that make sense? Because it's all those normal components. So this is the work done by F in the outward direction from D along the boundary. Boundary. Doesn't have an A yet. No. Yeah, boundary. That's a great word. Okay, so the total work done, kind of, that F is doing to pull that region apart along its boundary. You know, that's what this is, how this thing is getting pulled apart. We saw that that is exactly equal to the divergence of F in that region. Okay, so however much F is pulling this region at its boundary is exactly equal to how much that vector field is trying to expand within the boundary. Okay? And so this is kind of the sum of the, we'll call it like the expanding force of that. Okay, so that's kind of like the two relations between the curl and the divergence. And so another kind of interesting implication about this does is if we look, let me start that page. Okay, so one of them said that F dot over dr equals the vertical component of the curl of F, and the other one said that the normal component if we took the line integral of the normal vector, that's going to be equal to the integral of the divergence of that. Okay? And so what we can kind of compare these two is both the fundamental theorem for line integrals and the fundamental theorem just for calculus. And what I mean by that is that over here on the right-hand side, for both of these, we're taking the integral over a region of kind of, it's a little funny, but we kind of noticed that both of these involve derivatives. Both the curl and the divergence are kind of notions of rates of change of this vector field. So both of these are integrals over a region of, I'm just going to put it in parentheses, derivatives of this vector field. And then on both of them, over on the left-hand side, we're just evaluating the vector field itself. Along the bound of the region. Okay, and so, think back to the fundamental theorem of calculus. The fundamental theorem of calculus says that the integral over an entire interval, which is kind of like a one-dimensional region, the integral over that whole region of the derivative of a function is exactly equal to evaluating just that function at the boundary of that region. Okay, so this is like the one-dimensional, very most basic case, and now we've extended it kind of into two higher dimensions, or two kind of higher level versions of the same thing. So these are we can kind of think of these as being like three-dimensional or vector analogs of the fundamental theorem of calculus. And because vector fields are so funny, we kind of have to think of breaking them into the rotational portion and the radial portion, which is what the curl and the divergence are. And so we kind of get two different fundamental theorems for each. But that's kind of very, very interesting implication. And so that's kind of where we're going to, is we're going to keep building up more complex and interesting results relating the integral along a surface and the integral along a region with evaluating that function or that vector field or whatever it is just along the boundary. Okay, so kind of just continuing to extend the fundamental theorem into bigger and better places. Okay, so are there any questions about either of those? Kind of how that works. And so I think it's interesting because, like I said, what we've really done is we've rewritten Green's theorem. Because remember, again, Green's theorem relates the integral along the curve with the taking some derivatives and taking the integral within a bound within the region. And so we've kind of rewritten that into two different forms. But at the same time, I think that it also kind of gives us a little bit better understanding of what divergence curl represents. Because divergence is that outward, the vector field along the normal vector, and then the curl is the kind of the sum of the vector field along the tangential, going along the boundary. Okay? So